Thank you, Marcia, for this introduction, and thank you for inviting me. It's really a great pleasure and a great honor to be here. So we hope that the collaboration starts and will continue for a long term. We prognose that it will continue, we hope. So we predict that it will work correctly. So as you mentioned, I am a full professor at Tarbes National School of Engineering. It's in France we have engineering schools, écoles d'ingénieurs we call them, or institutes. It's a general school. So it's mechanical, material science, and industrial engineering. Inside we have also automation, robotics, computer science, etc. And I belong also, I am a member of the laboratory which is called in Production Engineering Laboratory, LGP, Laboratoire de Génie, Laboratoire Génie de Production in Tarbes, in the same. You have Tarbes here. Sorry, you see it there, and it's in the southwest of France, near Toulouse, near Bordeaux. Small town, small city, and also for those who practice, it's near Lourdes. Yeah, if you are looking for miracles, you find them there. Okay. So this is our school. Quickly speaking, the head is called our colleague who is full professor in robotics, Jean-Yves Fourquet. He is the head of this. Okay. Sorry, school. And this school will become a University of Technology. We are looking for the name, final name. We are looking because we cannot call it UTT because we have another UTT in France, Université de Technologie de Troyes. If you call it UTT of Tarbes, cannot. So we are looking for a name. It starts this University of Technology from September 1st. As I said, we are a general institute for engineering. We have first 2 years to prepare our students to have all common courses, maths, physics, mechanics, chemical things, industrial things. And then we have 3 years to become engineer. In the first year of these 3 years, it's general courses, and then they try to specialize themselves from 4th and 5th year. And we have 3 internships and also 1 mandatory mobility for international. They have to go for 1 semester abroad. We have inside this school our lab, which is a general also multidisciplinary lab, where we have also platforms to support our research. So platforms are for robotics, for computer science, for mechanical, for chemical, for material sciences. So and with also very developed recent means we use. Yeah, this is quickly. These are the countries where our students go abroad. It's really international. So you have just here some pictures. Tarbes here. You have Pic de Midi. It was the highest with observatory there, and also the city. And the research laboratory, as I said. The head is Bernard Archimède, who is a full professor in industrial engineering. I am the deputy director of this lab. It was created in the school in 1963, and the lab was created in 1989. We have more than 130 members with permanent, around 60 permanents. We have around also 60 PhDs, and the other staff is postdocs, technicians, engineers, and secretaries to support the research. As I said, it's a multidisciplinary research with, I would say, half for mechanical material science and half for industrial engineering in the large sense. That means industrial engineering, computer, robotics, automation, PHM, etc., etc. It's organized in 2 scientific departments. The first one for all things related to mechanics, and the second for all things related to systems. In the Department of Mechanics, Material Science and Processes, you have what we call research groups, 4 research groups, and we have 5 research groups in Department of System, and we have what we call transverse axis, which works for multi-disciplinary topics in the lab. Here you have the 4 groups of mechanical and material science. It's metallurgy, mechanics, structure, and damage. I will not go in details, but of course, I encourage you, if you would like to set collaborations, we are open for collaborations in all these domains for mechanical department or for system department. You can contact me and I can ask my colleagues to be in touch with you and collaborate. We have new links, design processes, sustainability in additive manufacturing. It's mostly additive manufacturing. We have interfaces, materials, polymers, assemblies, composites, and textiles. We have tribology, material science and processes, mechanics. I don't know if you are accustomed with this, but again, if you would like to collaborate, we'll be pleased to put you in touch with our colleagues. For system department, we have 5 groups, as I said. We have PICS, which is planning, interoperability, and coordination of systems dynamics. We have ACE, which is efficiency of electrical energy conversion systems. We have Mavericks for all automation robotics, methodologies for the design and control of mechatronic and robotic systems for interaction. We have another group which is ICE, Knowledge and Experience Engineering for the improvement of processes, systems and organizations. And we have the research group related to prognostics and risk safety management. The transverse axis works mainly on additive manufacturing, which is for all additive manufacturing processes, from material to systems. It tries to make together all colleagues from the 2 departments to work together. These are the platforms we have for mechanical, for material, for industrial engineering, for robotics. If you are interested in the equipments we have, you can come and we can share them. Of course, we ask for some agreements before to work on them. But we are really well equipped with recent equipment. So I finished just here to present you my lab, and now I will go to the presentation. Same for the presentation, I will not go to the details, but if you want to discuss, I will be pleased to do it with you. And of course, at the end of the presentation, don't hesitate to ask questions. This is for prognostics and health management, mainly because I am working on this. But as I said, for other topics in our lab, we will be really pleased to welcome you. I will present you the workflow, some approaches, and what we have done until now in the group. So, as you know, why we do this PHM is to try to anticipate failures, to predict failures, mainly, and then to try to optimize the maintenances. Mainly for us, it's condition-based maintenance and predictive maintenance. Okay? You have some statistics. I don't know if you have heard about this catastrophe, and there is a movie now from 2016, I think, something like that. And here, unfortunately, in Paris region, derailment of a train at the rush hour, and you have all statistics about the impact of degradations, failures on performances, on systems, on also costs. So we work in the group in PHM to try to anticipate these failures and try to reduce the costs. You have many definitions of PHM. I give you here only 3. one from transfer center, one from company, and one from research, pure research. If you look at these definitions, you will see that in PHM we work to use tools, methods, algorithms to monitor the system, to detect anomalies as soon as possible. This is very important. Diagnose the causes of the faults, and then predict what we call the remaining useful life. All this information, we use them to schedule optimally the maintenance actions. The process of PHM, of course, this is just to show the main steps. But what I mean is that we don't have to work, for example, on health assessment to go to the decision. We can, from health assessment, go directly to decision. Okay? We don't necessarily work all these steps sequentially. Okay? From data processing, we can go to anomaly detection or decision, etc., etc. But the main steps are here. We have a system here. You can replace this by your aircraft, and then we should first have representative data. Representative data, that means not only healthy data, but healthy and faulty data. This is very important. And then we pre-process this data. Why pre-processing? This is very, very challenging and important because most of works in academia, unfortunately, they work on sympathetic data, which are not real data, and then they do directly data processing, feature extraction, reduction, etc. But in practice, if you work on real systems, we are working, for example, for EDF in France, on turbines, these you have real data, and then you need to pre-process the data. That means you have to filter, to smooth, to complete the data, to remove outliers, to normalize, all these things. And then we do data processing. This is classical feature extraction, etc. And then anomaly detection, diagnostics to go to the cause of the failures, prognostics to predict the remaining useful life, and then use all this information to take decisions. I would like here to make the link between PHM and maintenance. As you know, I suppose that you are familiar with this. Okay, everyone. And then for us, we try to work on these two things, condition-based and predictive maintenance. Okay. What I wanted to show here is the difference between maintenance and PHM. In industrial, unfortunately, industrials, they confuse both of them. I don't know here, but at least in France, there are sometimes confusion. Some industrials, they think that predictive maintenance is PHM. For me, it's not the case. They are narrowly linked, of course, PHM and maintenance, predictive condition-based, but they are not the same. For me, PHM is a way to elaborate the methodologies, the algorithms, the tools to give information to maintenance, to do maintenance. That's why, for me, we have to separate. Here we elaborate the algorithms, the methods. At the output here we have information, remaining useful life, the cause of the failure, the time of failure, etc. And then we use this information to schedule maintenance actions, interventions. And then when we do maintenance on the system, we change the health state of the system. And by changing the health state of the system, we get new data at the input of the algorithms. And then the cycle continues like this. Okay, of course here I could add also all what we call supply chain, all to supply the spare parts, etc. Okay. The application of PHM, you know, you find it in aerospace, you find it in railway, automotive, you find it in wind turbines, in all equipment for printers, etc. You find it in manufacturing processes, and so on. Okay. This is, of course, not exhaustive. We don't have all here companies. Just to mention that for aerospace you have the main companies, the energy also, railway, etc., etc. So I didn't put KLM, sorry, but they are inside, of course. Okay, they are not looking, so you have to cut it after. Sorry, I'm laughing. Okay, it's not complete, of course. Huh? Here, just to show you the main failure types we have on a system. When you have a system, we have what we call physical failures. That means leakages, blockages, etc. on a system. You may have what we call also controller failures. They are control algorithms, okay, the controllers. You may have also actuators. You may have, at the end, sensors. We can calculate at each time the health indicator value. And then, because we have a threshold, we can estimate the remaining useful life of each MEMS. Of course, when you see here this blue line, we know it after each degradation. Because we are in a lab, for each MEMS we know. But when we predict, we don't put it. So we give only the data for the PhDs. They don't know this true value of rule. They know they have only the data. And then they try to predict, you see, look at the predictions. They are quite good predictions. And then all this we use it to, of course, to take decisions. We work in our group also, I didn't mention this, we work on how to use this information to make decisions. It's mainly optimization problems. And the decisions can be on two types. Operational, that means how to make maintenance interventions, how to change the perhaps the set point, the control. We can work also what we call fault tolerant control. I don't know if you have heard about this. That means when you have in aerospace, in aircrafts, it's well used because the aircraft should be tolerant to faults. When you have a failure, they should continue operating. When you have one engine which is out of service, they continue with one. Okay, they are called tolerant systems, fault tolerant systems. Control in the sense that when you have a fault, you try to manage the control to continue working even with the fault. Also the feedback, the decision can be the feedback to the design. That means we should, for example, add sensors, try to place other ways the sensors because they don't detect correctly. We can also redesign the components so that they can be easy to maintain, what we call maintainability. We take less time to maintain, etc., etc. We work on this. Okay? I can take 5 minutes to... Yeah. So here I will quickly speak about some steps, feature engineering, anomaly detection and diagnostics, and prognostics. Just some results. You have our papers, and of course we can discuss, we can continue by exchanging by emails. You have, I guess, worked on this. When you have raw signals, after pre-processing, after all this preparation of data, we extract features. We can scale the features, we can select the features, we can build health indicators. They are for us different steps. In
feature extraction domain, you have mainly three types of features: time domain features, frequency features, and time frequency features. I don't know if you have worked on this. And you have, of course, each one for each specification, each application. If you'd like to go further, you can look at this paper. It's, of course, for free. You can download it. Here, our first contribution on feature selection. We worked on with Alstom. Okay, there are some confidential issues I will not speak in details. Quickly speaking, we have a system for a train, TGV, and then we have some sensors, okay, temperature, vibration, and so on. And these are raw signals. Then we worked on a method based on a genetic algorithm to select the best features among the extracted ones. The best features for this only for detection and diagnostics. not for prognostics. Because when you select features, it depends for which purpose. Do you select for detection? Do you select for diagnostics? Do you select for prognostics? Do you select for maintenance, optimization, and so on? Okay, so we worked here for only anomaly detection and diagnostics. You can find the here you can see the results without selection and with selection. You see the separation here. Here you cannot separate the modes, the operating modes. Here. You can turn in all directions the points, the graphs, you cannot separate. And even by working with KPCA, with kernel methods, we cannot separate. But by using our algorithm, we can separate the modes. Another thing we have proposed is a health indicator we have proposed, which is also published here in this journal. The main idea is that we take a whole signal, we split it in parts, and then for each part, we calculate this amount, the signal divided by the maximum of the amplitude of A15. And then we build a health indicator based on the mean of the kurtosis and the variance. Okay. And this algorithm gives us very good results. You see here at the end for class separability. It works for many applications, but the other methods we have selected here, you find all the details in this paper. Okay. Also, you can read it and then we can discuss. If you have questions, we can work there. Sorry, this data now will be available soon because we just had recently last week an acceptance of our journal paper where we describe many data and we will share them. You will find the GitHub website to download, like the data we have at the NASA. But the advantage of this data, they are really real data. For example, for this one, it was like industrial platform, real data. We have worked on them. Okay, they will be for free. The second contribution in health indicator construction was this. It was a selection of features and build health indicator automatically. That means without human intervention. You give at the input the raw signals, at the output you get the health indicator which is best for prognostics. Okay? And by genetic algorithm, how it works? We take the signal and then same as previous, this signal will split it, but here the algorithm will split different sizes. With previous, it was fixed size of splitting. You have the signal, we split it in parts, and these parts are fixed length. Here, we choose many lengths. And also, we choose many features. And then the algorithm, by genetic algorithm, selects the best lengths and the best features. And combines these features automatically also by genetic algorithm, by different operators, plus, minus, division, and then finds the best health indicator by combining the features. Because if you look in this paper, you will find we have cited some selection methods and some methods to build health indicators. You have in literature some indicators which are built randomly. They tell you we take this feature, we divide it by the square of another feature. But they don't tell you why. They just tell you it gives good results, that's it. But with this, we have tried, the algorithm runs and tries all the combinations, many combinations, and gives you the best for prognostics. Okay? You have it here, and also we can provide the algorithm, the program, etc. Okay. We tried it on two data sets, turbofan engine from NASA and bearing data set. And you see here at the end the performance of our post-treated health indicator. Each time it's better. Okay. This is for prognostics also. For diagnostics, another before it was for feature extraction and selection, health indicator construction. Now for diagnostics, you have this method. I don't know if it's clear. Otherwise, you find it in this paper. The main idea is what? Is to combine both direct and indirect monitoring data. What we mean? We worked here on a robot used in machining to machining parts to produce mechanical parts. Usinage. You see machining? Yeah. And then in this robot, you have two kinds of sensors. You have sensors placed at the end, at the tool lever, machining tool, and you have sensors placed at the articulations of the robot. You know, those in the motors of the robot. Okay. So we have used both to do diagnostic. What is the advantage of this? First, we use only the data placed at the tool of the robot, machining tool, because it's easy to use those for articulations. You have to go to the automaton of the PLC of the robot, which is not accessible because you need to have the authorization of the provider, the manufacturer. Okay, things we got because we were allowed. By using these sensors, we first learn classes, but sometimes these classes are not sufficient to separate all the modes. So now, online, we come here, and then by using the sensors from the articulations, we try to build new classes because we have more data. And these classes, we use them to enrich these classes learned by the sensors placed at the tool level. And then we continue like this. It's a loop. Here you have indirect monitoring data, and here you have direct monitoring data. This is the application on the robot. It was in the industrial case. Yeah, the results, of course, are always good, but we can discuss. And for prognostics, we have worked with the Canadian company. Here, it was a paper production process to work on how to clean the pipes. Yes, the pipes used in this industry process. Okay, the remaining line here is not for to calculate the time to failure, but the time to clean. This is very important. And see, by the method we proposed, we can go until 105 days. No, sorry, hours. Sorry, not days, hours. And for the company, this is very huge. This is huge because they could plan the maintenance, the cleanings. Yeah. So that's it. Thank you for your attention. If you have questions.